Hello students, in this class I will discuss an important concept of organic chemistry that's called stereoisomar. Stereoisomar is also known as space isomer. Which arises due to special arrangement of atoms or groups around carbon atom. I am keeping in writing everything such that later on you can take note also. Now suppose, look at here, suppose in this case I have written CH3CH OH COOH. In this case the name will be same if I write it this way. Suppose if I write it this way, H over here, or I can put CH3 over here. I am explaining in the next page. Suppose CH3 CHOH COOH. And look at here, in this compound, it is irrespective of the way you write it, the name of the compound will be what? 2-hydroxypropanoic acid. But this is a saturated compound. Saturated compound means the carbon attached with 4 different groups. When a carbon attached with 4 different groups, this is known as saturated carbon. In saturated carbon, all the carbon are not in a plane, 2 in the plane, 1 above the plane, 1 below the plane. So there is actually 3-dimensional structure. Now, depending upon the arrangement of atoms or group around carbon atom, the same compound can rotate plane polarized light in 2 different ways. Can rotate plane polarized light in 2 different ways. If it rotates plane polarized light clockwise, it is called dextro, or if it rotates anti-clockwise, it's called levo. Now this compound, if I write different way, keeping the groups around the carbon atom in different way, all the name will be same, but only difference is that some of them rotate plane polarized light in the right hand direction, some of them rotate plane polarized light in the left hand direction. So optical rotation arises due to special arrangement of atoms or group around carbon atom, and this is a part of stereoisomer. So optical isomerism arises due to rotation of plane polarized light in 2 different ways, either clockwise or anti-clockwise for the same compound. Let us think of it. For optical isomerism, there is a precondition. Precondition is that the carbon should be saturated and should be bonded with 4 different atoms or group. The 4 different atoms or group linked to the carbon atom is known as chiral carbon. Look at here, it is writing this way: C, middle one CH3, COOH, OH, and H. You can write CH3 over here, CH2 over there. There is different way you can write it. But actually it is a 3-dimensional structure. 2 should be in the plane, 1 should be above the plane, 1 should be below the plane. So it is 3-dimensional structure. Different way of expressing 3-dimensional structure in 2 different ways are the 4 ways. Different way by which 3-dimensional structure can be represented two-dimensionally are as follows. One of them is called flying wedge. Everything I will explain. In this case, two in the plane, one above the plane, one below the plane. Look at here. Suppose COOH, CH3. This is written OH. This is called wedge. It is above the plane, and this is below the plane. It is the flying wedge representation of three-dimensional structure. All the carbon are in a plane. Most oxidized group is written on the top of the plane. OH is above the plane, H is below the plane. This is flying wedge form. One of them is called Fischer projection form. In Fischer projection form, the chiral carbon is which carbon? Written by asterisk mark. The group attached to it, 4 different groups, is known as the chiral carbon. In the chiral carbon, I have written a chiral carbon is written at the intersection of the horizontal and the vertical line. Just look at here. Suppose it is written this way, so CH3C COOH. COH was written on the top earlier one. Suppose it is OH, it is H. It is a chiral carbon having one chiral carbon. So you should write an intersection between a vertical and a horizontal line represent the chiral carbon. This represent the chiral carbon. CH3 was written here, COH over here, which is above the plane. Above the plane is written this way, and below the plane is written that way. Okay, this is the Fischer projection form of three-dimensional structure. Now, when you want to convert and flying wedge form, it is called flying wedge form. It is Fischer projection form. What is the way? First of all, depending upon the number of chiral atom, here represent the one chiral atom though. So in this case, it is represented at the intersection of the horizontal and vertical line. There will be one intersection as there is one chiral atom. If there is two chiral atom, there will be two such horizontal line, three chiral atom, three such horizontal line, like that. All the intersection between vertical and the horizontal line represent the chiral atom. Next part, what I want to tell you, CH3CCOH, it is on the top of the plane. This is in the plane. CH3CCOH will be in the plane. Now, wedge form should be right side of the vertical line. Wedge form, remember, wedge form should be right side of vertical line. Wedge form, right side of vertical line. And dash form would be left side of vertical line. This is the way of representing three-dimensional structure to two-dimensional structure. One of them is called flying wedge form, one of them is called Fischer projection form. Now, very interesting thing I will explain now. Right, look at the board properly for the next slide. Now we have written this though. CH3, COH. Here I have written OH over here, H over here. Irrespective of the position of C, this group can be represented by 4 different ways though. Either CH3 or H or OH or COH. This place can be filled by 4 ways. This place can be filled by 3 ways. This place can be filled by 2 ways. This place can be filled by 1 ways. So there is 24 such arrangement are possible. All these 24 arrangements should have the IUPAC name only. 2-hydroxypropanoic acid, because COH group is the main functional group, OH is in the second carbon atom. The longest chain is 3, it will be 2-hydroxypropanoic acid. Irrespective of the way, whether you put CH3 group on the top, bottom, left, right, that doesn't matter. Its name will be 2-hydroxypropanoic acid. But out of all these 24 arrangement, 12 of them can rotate plane polarized light in the right hand direction, which I called as plane polarized light. Plane polarized light. Right hand direction. Called dextrorotatory. Other 12 rotate plane polarized light in the left hand direction, called levorotatory. Now, direction of plane polarized light is an optical property. Looking at the compound, you are not in a position to find it. So there are two absolute configurations, that is known as R. R means which rotate plane polarized light in the right hand direction. On the other hand, which rotate plane polarized light in the left hand direction. Now, I told you one thing, how you convert feature projection, flying wedge form to feature projection form, or feature projection form to flying wedge form. Try to follow this part first, then I will discuss the absolute configuration out of this arrangement, which of them will rotate plane polarized light in the right hand direction and which will rotate plane polarized light in the left hand direction. Now suppose it is written this way. Suppose a compound is written this way. It is a carbon. It is written NH2. It is written OH. It is written Br. It is written Cl. It's a chiral carbon attached with 4 different groups. Now there is one chiral carbon, so I should put one intersection of horizontal and vertical line. Now NH2 group is in the wedge form, so it will be placed over here. Wedge group will be placed over here. Now Br over here, Cl over here. On the other hand, suppose in another case a feature projection form is given to you, you have to write down the flying wedge form. Now in this case it is written as Cl, in this case it is written as H, in this case it is written as Br. No problem. Just think of a chiral carbon. This is at the vertical of the horizontal line, so it will be placed on the top. Cl was placed on the bottom, it is dash Cl. Now NH2 over here, Br over here. So I have some idea how to convert feature wedge form to feature projection form to flying wedge form, or flying wedge form to feature projection form. There is one chiral carbon only, but if there is 2 chiral carbon atom only, how to do it? I will represent it this way. Look at here. You see, both this carbon are chiral carbon because both of them attached with 4 different groups. COH is a group, H is a group, OH is a group, then the whole is a group. Suppose it is 1 and 2, 3 and 4. Suppose they have written the feature projection form this way. COH, COH, OH, OH, H, H. Now, if I want to represent these things into the flying wedge form, suppose this carbon I want to represent this carbon, carbon number 2. How to do? H is on the right side, should be written this way. H over here. The whole group CHOH, COH should be written over here as a whole group, written together. Then COH over here, OH over here. This is the representation of three-dimensional Fisher projection form to flying wedge form. On the contrary, suppose the structure was written this way. This is the Fisher is given, flying projection you have to find out. Now suppose flying wedge is given, you have to write down the Fisher projection form. Or if it is the case of your third carbon, in which you have to convert the flying wedge form, how to represent it? In this case, the whole thing is written together, COH, OHH. Actually, I am doing it in the next page. Suppose it is written this way. For this carbon, I want to represent the Fisher projection form. So H will be above the plane, COH should be here, COH should be in the plane, H will be in the plane, OH will be in the plane. You just see COH, OH, H above the plane, the whole thing below the plane. Okay, now I have some idea about Fisher projection form and flying wedge form, how to convert Fisher wedge to flying wedge form or flying wedge to Fisher projection form. That part I told you. Why it is not in a plane? Because in tetrahedral compound, when a carbon attached with 4 different groups, 2 are in the plane, 1 above the plane, 1 below the plane. Hybridization is sp3 and bond angle is 109 degree 28 minutes. Now I have to determine the absolute configuration, either it is through flying wedge form or Fisher projection form. In order to determine absolute configuration R and S, we should stick to the following rules. Rules number 1, 4 different group around the carbon atom represented priority wise one, 2, 3, 4. Highest priority should have 1, lowest priority should have 4. The priority is defined as the atomic number of the element atom directly attached to benzene nucleus. Suppose think of the case of Fisher projection form. Suppose it is given H, it is Cl, it is Br, it is NH2. In this case, H is 1 atom, Cl is 1 atom, Br is 1 atom, NH2, N 1 atom, 2H is there. But the atom directly linked to the carbon are hydrogen, chlorine, bromine and nitrogen. So bromine has highest priority, that is 1, highest atomic mass, followed by chlorine, followed by third, and H. H is the lowest priority, Br is the first priority because bromine has atomic mass 1, hydrogen have atomic mass 4, so it is the lowest priority. Now, when the first atom, if there is more than one atom, first atoms are same, then I should move to the next atom to find the priority wise. Look at here, next example. Suppose it is given this way. COOH, CHO, CH2OH, CH3. Look at here, purposefully I have given the same atom carbon directly linked to the chiral carbon. Obviously I should go to the next one. In the next one, in this case COH, next one is C double bonded O. In this case, if I break it, it will be C double bonded OH, it will be C double bonded OH, it will be CH3, it will be CH2OH. Now C double bond O is same in both the cases. In this case, next is O, next is first atom next to the chiral carbon is C, then double bond O, both are same. Go to the next one because it is not yet defined. In this case it is O, in this case it is H. So it is the highest priority 1, it is the highest next priority 2. Out of these 2, After CH2 there is H, after CH2 there is O. So it is the third priority, it is the fourth priority. Is it clear? In case of double bond, is treated as the two atoms. In case of triple bond, it is considered as the three atoms. Look at here. Suppose it is given CN. Then your CH2OH. Then your CH3. Then your NH2. We should go to the next one. Next one is nitrogen is the highest one. So it will be the one. In this case, carbon, all of them are carbon, but in this case, carbon attached with 3 nitrogen. Each nitrogen is 14. So 3 nitrogen will be 42. And 42 is much greater than out of these two. So it will next, it will be the case of second one. In this case, it is the third one. In this case, it is the fourth one. So double bond is treated as the equivalent to 2 atom. Triple bond is treated as equivalent to 3 atom. In this case, priority is defined. Most important thing is to determine the priority. After that, you can find out the absolute configuration. Double bond equivalent to 2, triple bond equivalent to 3. In case of isotopic substituent, suppose same element have different isotope, higher atomic mass should have greater priority than that of the other. Okay, so these are very basic rule to determine the priority of the atoms or group around chiral atom. After that, what to do? Look at here, please. Suppose I have done the Fischer projection form of this. Out of 24 arrangement, it is one of the arrangement. In this case, whether it is rotate plane polarized light in the right or left, that I don't know, but I can find it out. How we can find it out? Two equivalent rotation is equal to the same optical rotation as that of the original compound. If I make two equivalent rotation, that means I can do this way. H was placed at the bottom, COH group is placed over here. It is one rotation, interchange of H and COH. Next make another interchange, OH group over here, CH3 over here. This is one of the rule to make lowest priority group at the bottom of the chain. This is one way of representing absolute configuration. Now, I don't know its absolute configuration, but if I know its configuration, then this configuration will be same as that of the after two equivalent rotation. What is the configuration? Absolute configuration. The original should have the same absolute configuration. In this case, priority wise, it is 1. In this case, after C double bonded O, so 2 oxygen, it will be 2, it will be 3, it will be 4. Forget about 4. 1, 2, 3. We are going anti-clockwise. So absolute configuration is S. So in this case, original it will be S. So what I have done, the Fischer project, and first I am discussing through Fischer projection form, then I should discuss through flying wedge form also. No hassle in it. But first of all, what to do? I just see OH, then COH, then CH3. For keep the 1, 2, 3. The 4 was at the bottom. We are moving anti-clockwise, so it is S. So optical so absolute configuration of the original compound should also be S. Now, if we make one interchange, not two, one interchange, then absolute configuration will be opposite to that of the original compound. If one rotation or odd number of rotation, even number of rotation gives same absolute configuration, odd rotation gives opposite of absolute configuration. Just I am writing that. Even number of rotation produce same optical isomer. Even number of rotation means 2, 4, 6, etc. Odd number of rotation produce opposite optical isomer. That means in case of odd number of rotation, R become S become R. But even number of rotation, R remains as R, S remains as S. Now I am showing these things also to you. Suppose just what we have done in this case, we have done this too. CH3, H, OH, COH. Suppose it is. Make two even rotation equal to what? OH over H over here, OH over there, interchange of H and OH is done. In this case COH, CH3. In this case it is 1, it is 2, it is 3. R. It is even transformation. Even transformation. If I do odd transformation, only H and OH if I do, what it will be? H will be over here, OH will be over here, CH3 over here, COH over here. Priority will have discussed 1, it will be 2, it will be 3, 1, 2, 3 are going anti-clockwise, so it will be S. So original compound was S. Because in this case two equivalent transformation was done though. So it is R. Original compound is R. Two transformation it become R. After one transformation it will be S. So these two are optical isomer. So 1, 2, 3. All has the same name, 2-hydroxypropanoic acid. 1, 2 are called, 1, 2 are identical. 1 and 2 are identical. And 1 and 3 are optical isomer. Is it clear? If I will give more such example, such that it will be more clearer to you. In this case, Fisher projection form, I have done the absolute configuration. Now with flying wedge form, I will determine the absolute configuration of the organic compound. It is a Fisher projection form I have done. Now look at here. Suppose it is written this way. In this case, now you can do it directly without converting to Fisher wedge form, or you can change to Fisher wedge form also. Here I am doing directly without converting to Fisher wedge form. Directly from the flying wedge form, I will determine the absolute configuration. What to do? In this case, I have to find out the priority of the groups. In this case, O has the highest atomic mass directly linked to the chiral carbon. It is the chiral carbon. So it will be 1, then it will be 2, and because of double bonded it will be 3, it will be 4. Then the rule is you should make two equivalent transformation such that the lowest priority group should be the bottom of the plane. In order to put the bottom of the plane, what to do? Fourth is the large priority. I am interchanging 2 and 4 first. CH3 over here, NH2 over here. Is it clear? CH3 over here, CH3 become bottom, NH3 occupy the CH3 and NH2 interchange their position. The position occupied by NH2 earlier was occupied by CH3 now, and the position occupied by CH3 occupied by NH2 now. Now again I make same transformation over here. So in this case it will be OH should be over here and COH group should comes over here. Now in this case it is 1, in this case it is 2, in this case it is 3. 1, 2, 3, S. So absolute configuration of the compound based on flying wedge form should be S. Now if I convert it into feature projection form, I will show you the actual configuration of the compound 1 should also be S. How to do it? Acha, see, this is the intersection. Now it is on the wedge right hand side. NH2 should be on the bottom one. Is it so? Now COH, CH3. It was 1, it was 2, it was 3, it was 4. Now I have interchanged the position between 2 and 4. So CH3 comes over here, NH2 gone over there, then OH comes over here, COH over here. Okay, now it was 1, it was 2, it was 3. So anti-clockwise it is S. I hope it is clear to you how to find out absolute configuration based on flying wedge form or feature projection form, and how to interchange flying wedge form to feature projection form. That part also I discussed. Now if I make one interchange, the original compound was S, and after interchange it will be R only. Okay, just do it. You have no need to believe on my words, just see that it's coming. It is COH, CH3, OH on the top of the plane, NH2 on the bottom of the plane. Just I am doing it this way. It was COH, it was CH3, OH was on the top of the plane, NH2 was on the bottom of the plane. Okay, now I'll do just one transformation. This position occupied by CH3, this position occupied by NH2. It was 1, it was 2, it was 3. Movement was this, R. If I do flying wedge form, what to do? This is the flying wedge. If I do feature projection form, it will be what? In this case, OH should be over here, NH2 at the bottom, CH3 over here, COH over here. If I do one transformation, what it will be? CH3 over here, NH2 over here, COH over here, OH over here. OH2, it is 1, it's 2, it's 3. Because O is the highest atomic mass, then nitrogen, then hydrogen. So it will be R. In this absolute configuration was determined. Okay. Now this is about how to find optical isomer R or S based on a organic compound having a chiral carbon. Next class I will discuss more of it.